Okay, we'll make a start now. So today what we are going to do is look at tutorial 4. So tutorial 3 we have done before, and the solutions of tutorial 3 has been uploaded in Blackboard. So if you go to the revision folder, and in the revision folder I am putting the lecture notes as well as the tutorial sets and the solutions as well. So number 3, sketching bending moment diagram, we have done quite a fair bit of number of problems. So we are going to do now today number 4. So number 4 is not qualitative but using a free body diagram to draw the bending moment and shear force diagram. So we'll try to do few problems today and then I'll upload the solution. So let's keep it there. So for the first problem, and then I'll probably midway through I'll talk about tomorrow's test and group coursework as well. Okay. So for the first problem is you have got a point load onto a simply supported beam. So point load on a simply supported beam is given as follows. So the reaction force we can easily calculate. In fact, these are the reaction forces. We have done it before into the first tutorial. So you have got this beam and then 7 meters. So tutorial number 1, you have found out these reaction forces. So if 5 kilonewton is there, then you can find out reaction force as 3.6 and 1.4. If not, take moment about either of these end support and then you will get the other reaction. Now we are going to draw bending moment and shear force diagram. So to draw the bending moment and shear force diagram, you don't need to write it up, so I'll upload the solution today after I go through, so you can see the solution, but you can have a look at that first. So if I take a cut at a distance x from the left, so somewhere here, then my diagram would look something like this. So if I take at a distance x, why do I take at a distance x? So that we can write an expression of shear force and bending moment. So if I take a section at a distance x before 5 kilonewton force, or in other words x is less than 2 meter, then I can get a section like this. Now of course wherever I have made a cut, I have to put a shear force and a bending moment. Now I'll use this sign convention. On the right hand side, positive shear force is upward. So I put a positive shear force upward, and bending moment is clockwise on the right hand side. So I put a clockwise bending moment on the right hand side. So I need to find out what is V and what is M by doing equilibrium analysis. So giving the vertical forces, summation of vertical forces 0, would give me V is equal to minus 3.6, because V must act downward to resist this 3.6 kilonewton. And moment at this point would be, so 3.6 times x plus m equal to 0. So that would be m equal to minus 3.6x. So if you take moment about this point, then what are the moments that would be acting? Moment due to this 3.6 kilonewton, and that will rotate the beam in the clockwise direction. So the moment due to 3.6 is 3.6 times x at a distance x from here. Now of course that's a positive, I am saying clockwise moment, so that is positive. And then of course I have got a moment at my point where bending moment already existing at a point that I have cut. So that is m equal to 0, because V doesn't give any moment because I am taking moment about this point. So that will give me m is minus 3.6x. So if I take a section x is less than 2 meters, these are my expression. Now if I take a section which is x greater than 2, or in other words, I've got a sections like this, then again I put wherever I take a section, I put v upward, that's a positive sign on the right hand side, and m in the clockwise direction, I put it there. So what is the shear force? So the shear force now will be, so v is upward, 3.6 is upward, so 3.6 upward shear force minus 5 plus v equal to 0. That's the summation of vertical forces here, keeping upward forces 0. So that would give me v equal to 1.4 kilonewton. So that's the shear force at any section x greater than 2. What about moment? If I take moment about this point, I have got moment due to 3.6 force, and that would be rotating my beam clockwise. So summation of moment about the section 0 would give me 3.6 times x. That will rotate my beam clockwise. So that's positive. What about 5 kilonewton? 5 kilonewton force will rotate my beam anti-clockwise. So that will come with a minus sign. And 5 times this distance. So this distance is x minus 2. And of course m is in the same direction. Plus m equal to 0. So that would give me m is equal to minus 3.6x plus 5 times x minus 2. So those are the two sections that you need to take, because other points it doesn't vary, doesn't have any other loads or anything else. So if we draw now the bending moment and the shear force diagram, this is what we will get. So for x less than 2, shear force is minus 3.6. So I put that in. For x greater than 2, plus 1.4. And then of course there is a jump there at this point here, which is the load. 3.6 plus 1.4 is 5 kilonewton. So you could see there is a jump under the concentrated load. What about bending moment diagram? M is minus 3.6x for x less than 2. So slope is 3 points. So I put the value of x equal to 0, bending moment 0. It will increase x value until 7.2. And then for x greater than 2, minus 3.6 plus 5x minus 2. So if you do that, then you'll get these expressions. So I'm just drawing these two lines over here. Now check whether you get the same result with dv dxw and dm dxv or not. So dv dxw means slope of the shear force diagram is the load, which is fine. We get the 3.6 in this part, and then in this part is 3.6 minus 5, so 1.4. So that's okay. And there is no change in the load in this part. So slope is 0. Bending moment slope is the shear force. So here slope is 3.6 minus 3.6. We get that. And in fact it is so minus 3.6x. This part slope would be plus 1.4. We get that as well. So also you can see 1.4 times 5. Now of course this is 7.2, does not mean much, because these reaction forces are not exactly 3.6, because 7 is a very odd number in a way. So if you divide 5 by 7, there would be a few other decimal places I needed to consider. So it's 1.4 times 5 doesn't quite make 7.2. Or in other words, this is really not 1.4. It will be something 1.4 times something, 1.44 or similar. Okay, so you get that idea that you take a section and then you draw the shear force and bending moment diagram. Okay, so if I go to the next problem is again the same set of problems from tutorial 1. Now this time we are doing the shear force and bending moment diagram. So I take problem 2 now. Again, I'll give you the solution in there, so don't worry about the noting it down or anything. So in this case, what do I get? I've got this beam again. So the total load would be 10 kilonewton acting at a midpoint. So the reaction forces are 3.6 and 6.4. So if I take a section up to here, say before the load starts. So if I take a section up to here, then I'll have a shear force at any point like this. So that's V. And I'll also have a bending moment, which is M. Now what would be that expressions now? So if this distance is x from the left hand side, so V plus 3.6 is equal to 0. So V equal to minus 3.6. And what about M? Now 3.6 will create a clockwise moment. So 3.6 times x, and M is also clockwise to 0. So that would give minus 3.6x. So in fact that is what we get for x less than 2. Now if I go slightly further down, we take x more than 2 meter. So when it goes into the uniformly distributed load category. So if we take a section at this point now, then I have got let me use the right side. So I've got this shear force V, and this is, so wherever you are taking a virtual cut, you have to remember that within the cross section internally there is a possibility of a shear force and a bending moment. We don't know what's the value. So it's almost like cutting a truss. So whenever you have a cut, you have to replace that with a force that may exist at that point. It may be 0, but may not be. So we have to assume that there is a force in there. In this case, for a beam, shear force and bending moment. So whenever we make a cut, we have to assume there is a shear force and there is a bending moment internally acting. And this shear force and bending moment internally acting is so we have sort of we have exposed it to make it keep it under equilibrium. So if we do the equilibrium now, what do we get? So 3.6 goes upward, so that's load. 2 kilonewton times, how much is the distance? This is 2 and that is x. So 2 kilonewton times x minus 2, that's downward. So I put it with a negative sign. And V is upward, so that equal to 0. So that will give you 3.6 minus 2x plus 4 plus V equal to 0. So this should be 7.6 minus 2x. So V you will get 2x minus 7.6. So that's the expression of V. What about bending moment? Now bending moment, as before, we will calculate. So load by load we will calculate. Bending moment while calculating, taking a moment equilibrium we will calculate. So I'll take a moment equilibrium about this point, about point x. I'll say 0. So I'm taking moment about this point. What are the forces? Forces are this force, this UDL, this shear force, and a moment acting inside the cross section. So moment about point x equal to 0 if I take, so let's take one by one. So 3.6 about this point. When you are taking moment, forget about anything else, any other support or anything. Just see which direction that force will rotate your structure. Is it clockwise or anti-clockwise? And according to a sign convention, add a plus or minus. So 3.6 will rotate the beam about this point in this direction. So I'll say 3.6 times the distance is x, and moment is always force times the distance. So that is clockwise, I'll say that is positive, okay? 3.6 times x. What about this load? Now that load, how much is the load first of all? The load is 2 kilonewton per meter and over a distance of x minus 2. So this distance is x minus 2. So the total load is 2 times x minus 2. So that is the load acting at that point. Where this will load act? This load will act because this is a uniformly distributed load. So 2 times x minus 2 will act through the middle. So you can think about this total load is 2 times x minus 2. Why 2? 2 kilonewton per meter. That's what it is coming from. So this is 2 kilonewton per meter. And x minus 2 is the length of that uniformly distributed load. And that will act through the middle. So next, when I'm calculating the moment, so moment we need two things, the load, which is this bit. So this is the load. And we need the distance per moment. Now this will act halfway down there. Now total distance is x minus 2. So the moment will act as a distance x minus 2 over 2. So half of that distance. So this is the moment. Third thing, so to calculate moment for a force, you find out what is the force. If it is a direct point load, that's fine, that's the force. If it is UDL or triangularly distributed load, find out what is the total force. Second thing, find out where they are acting. So this UDL will act through its center of the load train, which is in the middle. So the distance is x minus 2 over 2. And the third thing then you consider whether that is causing which direction it will rotate. So this is the beam, that load will rotate the beam in the anti-clockwise manner. So this would come with a negative sign. And finally I have got moment due to V, that would be 0 because I am taking moment about that point. So although the V has got a value, but the distance for the moment is 0, so that would be 0. And then M is plus M is. So this is my moment equations I get. So again it looks complicated, but especially this UDL bit. But if you do step by step, moment due to the force is, first of all find what is the force. So here it is 2 times x minus 2. Find out where it is acting. It is acting half the distance of x minus 2. So x minus 2 over 2. And then see whether this is clockwise or anti-clockwise. Three things. If it is not a point load. If it is a point load, so this is itself is the load. So 3.6. It is acting at a distance x. So x. And then it is a clockwise or anti-clockwise. So these three things you need to consider. So if you do the simplifications, you get moment expressions as follows. So the moment expression would be x square minus 7.66 plus 4 for x greater than 2 meter. So can we draw them? Yes, of course we can. So for the first case, for the shear force, for x less than 2, shear force starts with minus 3.6. You get that? Up to x. And then minus 3.6 plus 2 times x minus 2. So when x is 2, then this part is 0. So that means at x equal to 2 it is minus 3.6. Now when x is 3, then this part is 2, 2 minus 3.6, so minus 1.6, like that, until 6.4. So you can find out location of 0 shear force by putting this V equal to 0, then you'll get x equal to 3.8 meter, that would be a 0 shear force. Which is useful because 0 shear force means bending moment will have a 0 slope. So that means bending moment is likely to have a maximum value at that location. So bending moment expression if I draw now, first bit until x to 2, it is a straight line because 3.6 times x. So it increases as a straight line. So this bit is a straight line. So this is a straight line. This is linear. Next part for x greater than 2, it will be this expression x square minus 7.6 plus 4, 7.6x plus 4 square. So put in few values of x and then you'll get this curve. And you'll see it will be maximum at x equal to 3.8 meter. Why? Because the shear force is 0. So the slope is 0 at this point. So that would be maximum bending moment. So m at p could be, if you put x equal to 3.8 meter, then you'll get minus 10.4. Also you can put directly, if you're doing it in Excel, so put the various values of x, and then you can find out different parts of, different values of bending moment. Now, in terms of, yes, v, you can integrate for these cases because it is 0 in this case. So you can integrate it to get this thing. Yeah, definitely you can. You can integrate it. And it is in this case. For example, here I'm saying this is 7.2. So if you integrate from here to here, that is minus 3.6 times 2. So it's minus 7.2. So at this point it is 7.2. But be careful, we are starting with the boundary 0. If it is not, if it is a fixed end, then you have to take care of these boundary values, the limit values. Okay. Is this okay? If you understand this bit, the other parts are just simply following this process. And it is nothing more than, in terms of the conceptually, it's no more difficult. So I'm going to do one more problem, and then I'll go to the coursework, tomorrow's test, and come back to it. I'll do one more problem. Is there any question on this one? Yeah? No. Is it okay? Okay. That end, is it okay? Good. I'll upload the solution anyway, so no need to copy or anything. Problem number 3. Again, this problem has been taken from tutorial set 1. So it's exactly similar. So what I'm doing now is I'll take a section at a distance x again. So if I take a section at a distance x now, so let's say this is at a section x. So I'll take a cut v and moment m. So putting the vertical equilibrium equation, I could say 1.4 goes down, so minus 1.4, v goes up, plus v equal to 0. So that gives me v is equal to 1.4 kilonewton. So for x less than 2 meter. So this is x less than 2 meter. What about the moment? Again, I've got 3 sort of generalized force, 1.4 V and M. So first one is 1.4 kilonewton, and I'm taking moment about x point equal to 0. So 1.4 will create an anti-clockwise rotation. So 1.4 times x, and it is anti-clockwise, so I'll put it a negative sign. V doesn't create any moment because I'm taking moment where the V is acting, so distance is 0. M is clockwise, so plus M equal to 0. So this gives me M is equal to 1.4x. So that's my first set when x is less than 2 meter. Now when I take slightly higher, let's say now I take x is here, for example, beyond 10 kilonewton meter moment. So if I take now, which is x greater than 2 meter, if I take x greater than 2 meter, a section, again as soon as I've cut it, I'll put it with 2 force, 1 shear force and 1 bending moment. So the shear force expression would remain the same, 1.4 kilonewton downward plus V equal to 0, so that will give me V equal to 1.4 kilonewton. So that does not change because this moment does not come into the force calculation. Now the moment about point x equal to 0, now let's see, 1.4 is still there, so it is rotating it in a clockwise, anti-clockwise direction. So again, just take the effect of a single load at a time, one at a time. So 1.4 kilonewton, about the point you are taking moment, think how or find out how this is going to rotate your structures, that load. So this is going to rotate your structure anti-clockwise way about that point. So put a pivot or a hinge at this point and put that load and see which way it will move. It will rotate in an anti-clockwise direction. So minus 1.4 times x. X is the distance from here to here. So x is this distance. So minus 1.4 times x. Okay. Now, then 10 kilonewton acting clockwise, that's moment itself. So that will clockwise, that will go 10 there. Now, for it is already a moment, it doesn't, we don't need to multiply that with the distance because that value is the moment itself. So in the moment equation they come as it is, only thing is with the sign, the third bit. So you need to check whether that is positive or negative, and that's it. You don't need to multiply that with any distance or not, because that's not a force, that's a moment itself. And then like similarly m here, that is clockwise, this equal to 0. So m would be 1.4x minus 10. So these are the two expressions for x greater than 2 and x less than 2 meter, and you can plot those over here. So 1.4 kilonewton there, and bending moment is 1.4x for x less than 2 meter and 1.4x minus 10 for x greater than 2 meter. Now you could see one thing, that the formula that we already know is first of all dv dx is w. So the load is, there is no load, no vertical load. So the slope is 0. That's okay. Then moment slope is shear force. Now we can see that the same slope, 1.4. So over 2 meter is 1.4. So this slope is 1.4. And that slope is also 1.4. So the same as the shear force. So in particular that's a positive 1.4. Okay. So dm dx is v, so the slope does not change. And here it changes bending moment because of this 10 kilonewton meter moment acting at that point. So that covers, I'll probably next do this G. Yeah, go on. Yeah, that I said, because if you divide 10 over 7, it's not exactly 1.4. So if you keep couple of other decimal places, that should match up to 0. Now, one thing is this point has to be 0 because that's a hinge. So if it's 10 over 7, 7 is not a right number to do this calculation. So it should be 1.43 or something. So if you take that, and then it would be okay. Then you should get the right one. Okay, so any question on this one? No? Okay, I'll come back to it. Probably I'll do problem G, because or maybe F and G. G first and then F. But I'm going to go through few things first. So let me go to the student mode here. So this is what you will see. What I have done is I have put this revision folder, and in revision folder I put the lecture notes so far. Part 2 is what you will be tested tomorrow. So part 2 is the truss, and this is what you will be tested tomorrow. So go through that. One of the things many of you have asked me today was that if you have got a truss, whatever, and you have got a member like this here, then I say this is a zero force member. Zero force member. Why? Because if you take this joint, for example, and then you draw that joint a little bit big, let's say you draw that joint. Now, the force in that member would be this, force in this member would be this, force in this member would be this. Now, these could balance each other. So there could be some forces in this member. Whereas if at all there is any force in this member, there is nothing to balance this at this point. So this member must be zero force. And funnily enough, it doesn't have to be 90 degree. So imagine you have got a truss, something like this, for example, and another member acts maybe like this. So if you take that joint, for example, so you have this joint, you have got one member would be like that, another member is in this way, and the third member goes that way. Okay, so you have got three forces acting at that joint. So this member would be zero force. Why? If there was any force in this member, then at that joint this member would create a component which is perpendicular to these two members. There is nothing. So these two members cannot resist that perpendicular component. No way to resist that, unless there is a force acting at that point. If there is a force acting each of these points, then of course things would be different. Then that force could compensate that. But if there is no force acting, so even if a member is, if one member is inclined, so if at a point there are three members connected, and two of them are parallel to each other, two of them along the same line, the third one would be zero. Now, that doesn't mean that if you have got a, so this would be a zero force member. Now, if at a point you have got three members like this, for example. Now, that doesn't mean each of these would be zero or any of these would be zero. Because if you take the joint here and draw them, for example, so you have got one member goes that way, another member goes that way, another member goes that way, for example. So you have got three forces. So horizontal component can be taken by horizontal component of that. Vertical component of this can be taken by vertical component of that. Okay. So if they are not, two of them not along the same line, you cannot, it's not very obvious that whether something would be zero force member. But if you ever see a member like this, another member connects like that, or another member like this, another truss member connects like this, so this would be zero force member. So this would be definitely zero force member. So that is a quick way to spot. Okay? And that you need to pick up in here. So similarly here, you could say that the both these two members would be zero force member. Because if you consider equilibrium of this joint over here, then it cannot be any force in this member, because nothing is there to take the horizontal one and nothing is there to take the vertical one. So both these two members would be zero force member. So this load must go through that member and this member. Okay? So if two or three members connect at a point, then you can find out quickly whether that would be zero force member. So in this problem, AB would be zero force member. Similarly, these would be zero force member. For other members, we are not so sure. It may be, it may not be. For example, this vertical member, it connects at the top, so, and there is a load, so this can take vertical load, so not necessarily this would be zero, and the inclined member may not be zero. or maybe 0, but we cannot really say that which one is 0 or not. So there could be some questions related to this 0 force member tomorrow, and I will be careful about the time. I know first online test some of you struggled with time, so I'll make sure that you get plenty of time. So, but that doesn't mean you'll get unlimited. It will be just right amount of time. Okay, so it won't be like you can finish that in 10 minutes. No, it won't be. So it will be. It should be, if you have revised well, 30 minutes should be enough. Okay. So what I've done is, so structures part 2 is all the lecture notes there, and then tutorial and the solutions are there. And also the other tutorial problems that were supposed to be in the class, that is also in the weekly sets in there. In terms of the group coursework, it's 20% this group coursework. And so first is the groups in here. So by tomorrow 11:30, those of you who wants to make your own group, please sign up to a particular one. So maybe pick up a blank one where there is nothing there. So maybe use a sign up one and then put your member's name in there. So sign up to have one, and if somebody is left from after tomorrow midnight, then I will assign you to a group. Coursework brief is given. Peer review is something that if you see that not everybody put in the enough equal effort, then you need to fill it in. Okay? And you need to fill it in and then send it to me by email, informing everybody. Okay, so instruction is given. And I think if you want to submit, if you go to the submission link, then you can see that. So this is the submission link. So you need to submit via this link. So you need to submit this via this link, and the rubric is given. How it will be marked. Quiet please. Quiet please. I've got a very bad cold, I cannot shout, so quiet. Sorry, I've got a very bad cold, I cannot shout, so please quiet down. So you can see the rubric. The marks are as follows: abstraction and conceptualization 15%, creativity 15%, calculation 50%, and presentation 20%. And then you put in your files. You can submit multiple times, but I'll pick up the last one. Now, next is the deadline. Is this deadline okay? Now, according to the published timetable, I'm 1 week late. So is 13th December okay? So that's the last week, Monday. Any concern about the deadline? So this should be okay, 13th of December? Okay. I normally don't like changing it later stage. So please can you review your other course units and the coursework submission and bring it and discuss it tomorrow if this date is not right or you want me to change. Because I would rather change it now so that not to penalize the students who have done it and submitted by the deadline, and then I change it on the last day, give another week. So that's not fair. So I'll give the time now. So let me know by tomorrow during the class if this red line is okay or not. Okay. In terms of tomorrow's test, there could be a couple of calculations, could be there, and maybe finding zero force member and some other calculations. So scope wise it's very similar to the first test, and those of you who cannot be here tomorrow, please fill in the mitigating circumstances form, because I cannot have this test at your home or off-site, because it is very much like the invigilated test here. So I try to maintain that way, and your final exam would be exactly very similar. You'll be taking to a computer cluster in January, not on your own, but in own computer, but in a computer cluster in January. So it will prepare you for that. Okay, so I will. Any other questions about the test or anything? So the question from that end was whether what? Structure stable. You mean the data table? About structure is stable or not? Possible. So this is a good point. Somebody asked whether a structure, whether there will be a question of some structure is stable or not. So if you have got a truss, thank you. So somebody said whether I am going to ask if a structure is stable or not. Now imagine there is a truss like this, and under a load maybe somewhat here, and then I say, okay, one of these is a cable rather than a bar. So cable can only take tension. No compression. So if this structure gets under compression for a load, then that will not be stable. Okay, so that bit probably you have to see that whether the force is compression or tension. So cable is like a rope that cannot take compression, but for tension it will be fine. It could be also, I could give you a truss something like this and put a load. Now you could clearly see that this should go like that. So this is a mechanism. So this is not a structure. not a stable structure. So this would be obvious in that. So I may give that type of little problem, that whether it is coarse or not. Okay, so what the group coursework peer review is, it's quite sensitive. I would like all of you to contribute equally, and I am expecting you to have approximately 20 hours per person, approximately, contribution. No more than that, 20 hours per person. So if somebody doesn't do that, then what you need is state that clearly that this person did not contribute. I'll have a chat with the group. Okay. Any other question? Okay, see you tomorrow then, and prepare and be well. If there is any question, put in the discussion board. Sorry.
How is it 15 times 1 possibility like this one?
So let me see, all members on 1 meter, right? So summation about moment A equal to 0 is here. So that would be 15 times, yeah, 1 cos 30 is 0.5.
Okay. And the cos 30, how is it cos 30?
15 times 1, and this angle is 60, so that is 30. So now cos 30 is not high, cos 30 is root 3 by 2. So if this is 1, this is equilateral triangle, so this is 60, this is 30 degrees. So this distance is 1 cosine theta, which is root 3 over.
So we were finding this line.
Yes, this distance, because that's what the moment of this force would be force times this distance, right?
Okay, thank you, sir. Will there be negative marking on this test?
I don't think so.
No.
But if it is, it will be clearly stated that this question has got negative mark.
Thank you.
I joined the wrong group by accident, and I want to know if I can remove you.
I can remove you now.
Yeah, could I? I'm in group 1.
You are in group 1.
Yeah.
So,
Barbara, yeah.
yeah, you don't want to be that?
No.
Thank you. I feel like I'm gonna end up
Okay.
like random.
You mentioned that if there's a square and there's no triangles, then the structure is unstable.
Yeah.
And in what circumstances we will find the square, because usually
You will not find these one unless you are forming a mechanism like in a car parts or something, where you want to have that movement, for example. In a mechanical assembly, it would have that system.
So if there is a member like this,
Then that will stop.
and this member cannot be 0, because otherwise the structure
So
would be
if there was member like this and another member like that cannot be formed like that.
So this
because
one
then that
cannot
will
be
take the
0.
force. No, that will take the force. That will not let it move that way.
Yeah, but this member cannot be a 0 force member,
No.
because otherwise.
For that load. Yeah.
Yeah.
But it'll have 0 force members in that bottom one.
So if there is no load here, these two be 0%. Right?
Like the same load in that one and that one.
So if there is a load here, then that is not 0% member.
But then
This could be 0% member.
What are the 0 force in it?
So if there is only one load here, this is a 0% member.
That's a 0.
that is a zero force member.
And
But-
then on the other side.
If you consider here, there will be horizontal and vertical reaction, so nothing else you could say zero force.
Well, if there's no support there, then it would be a zero.
If there is no roller, no pin but a roller, yeah, then that would be.
Oh, so the second one's a roller then.
Both are pinned, I put. So two reaction forces.
What if the other
One is roller, then of course horizontal member would be zero.
which one's zero?
So if there is nothing like this, then that would be zero force member.
Why is that?
Because if you take this joint, then you have got a vertical member, reaction force, and the horizontal member. So this member can take that reaction force, but there is nothing that will take.
Yeah.
So just look at the joint. And then you'll see.
Yeah, I just had a question about secretary release. About this question.
Yeah.
When I was doing it, because they wanted that, like, to find the LO member,
Yeah.
I decided to take my cut around here. But you in the. you
Yeah,
took it
because
around-
if you do any other way, then
Yeah.
you'll have more unknowns. Then it will not be able to solve.
So if you take the cut here and you just have this unknown and these forces,
then
it's
it's
not,
not able
wrong.
to solve.
It's wrong.
Not wrong, but you'll not get the solution.
I was able to get 98,
You get? Okay.
but it was wrong.
And
Then you are not probably taking all the forces correctly.
Thank you.
So, here's the dome, and if I cut it here, so that have a reaction force like that and a horizontal force like that, then will the